Hi everyone. In this video, we're going to wrap up chapter 5 by doing a lot of examples with some new and specific forces. So to review what we talked about last lecture before the exam, I introduced to you two types of frictional forces, the static friction and the kinetic friction. They're both a frictional force, so they're both going to point in the direction opposite to the motion, but one is going to show up when an object is not moving, and another will show up once the object is in motion. So, as I'm sure you've guessed, static friction is the frictional force that appears on a free body diagram of an object that is not moving. Okay, it is not yet in motion. And the magnitude of that frictional force is going to be mu s, which is the static coefficient of friction, times the normal force. Once that object starts to move, okay, it's going to have a frictional force equal to the kinetic friction, which is the kinetic friction coefficient times the normal force. So when you're doing a problem that involves friction, you must first see if the object is moving yet or not in order to know which term to use. So in this diagram, I showed it to you kind of right at the end of class. It basically shows you the relationship between the static frictional force magnitude and the kinetic frictional force magnitude. So the static frictional force magnitude, it can actually change depending on how much force is being applied, okay? Like how much tension is being applied to the block. So this magnitude will change depending on this. However, the kinetic frictional force is going to be a constant value. This is roughly constant. And it does not necessarily depend on the strength of the pull because it's already moving. The box is already moving. And the other thing to note is that the magnitude of the kinetic frictional force is always going to be smaller than the maximum static frictional force. So we looked at some materials and their coefficients. And I believe we did this example, since I have it already worked out, right? We did this example towards the end of class, so review it. In this example, let me just give you some kind of broad strokes information here. We had to use both the X and the Y applications of Newton's first law in order to solve this problem. And that was because, remember, the static frictional force includes the normal force. So we had to use the Y to find the value of the normal force. So that is something you're going to expect whenever you're doing a problem with friction. You're going to need both the X and the Y to solve this problem, and you're going to use information from the Y and plug it into the X. We also did this example really quickly towards the end of class, and I want to take a minute to talk about it here. So in this example, we're illustrating that the static frictional force, it can take any value up into and equal to its maximum value. And the value that the static frictional force will have, so the value or the magnitude of Fs, it's going to be equal to, it can take on any value up into and equal to the maximum value. And the value or the magnitude of the static frictional force, well, it's going to equal whatever force is being applied before it moves. And what's the mathematical reason for that? Because we're applying Newton's first law to all the forces in the X whenever we're dealing with static frictional force, right? It's not moving. So the sum of all the forces is going to equal 0. And that simply allows you to solve for Fs in terms of whatever the heck the force you are applying to that object is, right? Fs will simply equal F. So if we're not applying enough force to get that box to move, well, whatever force we apply, the frictional force, the static frictional force will be equal to that, okay? And it's only when that box starts to move that the force that you exert on the box may be bigger than the frictional force. But when the box is not moving, you are using Newton's first law to solve for the frictional force, and therefore it will simply be equal to whatever force you are applying at that moment. So let's do this example, and we're going to see something happen in the y direction. Okay, the normal force is not always going to be equal to the weight, and this example is going to illustrate that. So let me jump over to another screen here where we can work out example 515. So we're pulling on a box or a crate with a rope, but that rope has like an upward tilt to it, okay? And that upward tilt is 30 degrees above the horizontal. The question is, how hard should we pull this crate to keep it moving with a constant velocity? And we're given the coefficient of kinetic friction. So we're talking about a moving crate, right? So we're going to be using kinetic friction. So let's go ahead and draw the free body diagram of the crate, and I'll draw it right here. So we have the crate's weight, and then we have the crate's normal force. And then we have a force of tension on the rope pulling the crate, and that's at a 30-degree angle. I'll call that T. You can call it T or F. So those are all the forces acting. Oh, can't forget the most important one, the frictional force, right? Acting opposite to the direction of the motion. So the motion is occurring along the x-axis, right? So the frictional force is going to point along the negative x direction. So here's our free body diagram, and it's time for us to add up all the x's and the y's. And I note right now, I'm just going to draw it, the x and the y component of the tension, right? It's off at an angle, so it's going to have an x component, and it's going to have a y component. And I can right now just write down the magnitudes of the x and the y component. It's going to be magnitude of that pull, cosine 30. And then for the y component, magnitude of the pull, sine 30. Okay, and they're both positive. So we don't know the pull. We're trying to find the pull, right? We're trying to find T. Trying to find T. So let's set up our Newton's first law, right? Because it's moving at a constant velocity, so it's in equilibrium. So we're going to apply Newton's first law. Sum of all the forces in the x are going to equal 0. So what are all those forces in the x? Well, we have our negative Fk, and then we have our tension in the x direction, which is positive. And that's about it for the x direction. So Fk, we know its form, right? Its form is mu k times the normal force. And so let's leave it like that for now. Let's add up the forces in the y. All right, we got quite a few. We're going to have the normal force positive. We're going to have the weight force negative. And we're going to have also the y component of the tension. And now you're going to see what I mentioned before is that the normal force is not always equal to the weight. If you're applying any kind of force on that object in the y direction, you're going to reduce the normal force, right? So there is a tension in the y to the rope, and we're going to be reducing that normal force. So the normal force is no longer equal to simply the weight. The normal force is now going to be equal to the weight minus Ty. Okay, where Ty is T sine 30. So we're solving for T. Here's one expression with T in it. here is another expression for t in it. Let me go ahead and just solve for that. Let's write what tx is. T cosine 30. And that's equal to mu kn if I just move that mu kn over to this side, right? So I have two expressions with t in it, and then I have two unknowns, right? This guy's an unknown, and t is an unknown. So what I can do is I have two equations, two unknowns. I can solve for one of them and plug it into the other. So I'm going to solve here for n, which I already did, and I'm going to plug that n into here so that I can eliminate those unknowns. So I'm going to have t cosine 30 equals mu k, plugging in all that for n, weight minus t sine 30. Okay. And what is, I could plug in mg for the weight. We're not given the mass, so technically that's an unknown, but I think we're supposed to be finding finding t in terms of weight. I think weight is, although it's not given to us, it's technically a known, I guess. We're going to be given our answer in terms of weight. So let's just leave it as w for now. I'm going to group all my t's, what I'm solving for, onto one side. So that's going to leave me, if I distribute this, if I do all the algebra steps, I'll do mu k in the front. Okay, I distributed that. All right, and then let's move our t over. So we have t cosine 30 plus mu k t sine 30 equals mu kw. Okay, pull the t out. Oh, getting rid of that t. And then I will divide to solve for t, the tension, or the force that I need to pull with in order to keep that box moving at a constant velocity. And then I can plug in what they gave us for mu k, which was 0.4 times the weight over 0.4, cosine 30 plus 0.4 times sine 30. And I can get a value for that. And I can express the tension I need to pull on that rope with in terms of the weight of the crate itself. So 0.4 divided by cosine 30 plus 0.4 sine 30. Let's make sure I put enough parentheses in there. Oh, missing one right there. And so that becomes 0.375 times the weight. So the amount of tension or the amount of force I need to apply to that rope to keep that crate moving at a constant velocity to overcome the friction is going to be, roughly 37% of the weight of that crate itself. Okay, so let's zoom out and look at the problem solving steps here that we did, right? We needed to use both the x and the y, apply Newton's first law to both the x and the y, and the normal force is no longer the weight, just simply the weight, right? Now that we have an extra force in the y direction from the tension in the rope, that normal force is going to reduce down a little bit. And so we use that to solve for our unknown t. Since the normal force is also unknown, right? And that's just one variable we're going to eliminate so that we can solve for the actual point of the question, which is to find the value of that force that we need to to apply. Okay, so let's go back to the lecture. We're going to do another example. So now let's take a look at friction along an inclined surface. Okay, so here we are together, we're at Snowcat Ridge, and we're sliding down the hill, and now, you know, the snow is beginning to melt, and there's some friction there in between our toboggan and the hill. So what is the angle? All right, so now the question is being asked slightly differently. Now we want to know what is the angle, okay, of that incline. If we have a coefficient of kinetic friction mu k, okay, and the weight of us in the toboggan is W. And so this is going to be an algebraic. I know you guys kind of don't like it. I mean, they're fun. You should get used to algebra. Okay, it's all going to be algebraic here. And let's note some other important properties of this problem. We're moving with constant velocity here. So not only are we using kinetic friction because of that, but we're using Newton's first law because we're moving at constant velocity. So technically we're in equilibrium since we're not accelerating. So we're going to solve for the angle alpha now. So let's do this example. All right, so let's draw a free body diagram of us together on the toboggan. I'll draw that right over here. And with a free body diagram that's on an incline, I like to draw the incline as well. All right, so the weight of all of us together is going to be straight down. The normal force is going to be perpendicular to the inclined surface. The frictional force, what direction is that going to point? It points opposite to the direction of motion. And our motion, remember when we're doing an incline, we like to tilt our XY axis so that our x-axis is the inclined plane. And so therefore our frictional force is going to go in the negative x direction. And that is all the forces, right? So we're just sliding down due to gravity. Nothing's pulling us, so there's no tension at all. And we have this angle alpha, and we know the weight vector, that's the only vector that's not on an x or a y axis. So the weight vector is going to have a y component, and it's going to have an x component. And the angle alpha it's a similar triangle to this right triangle created by the weight vector. And the right angle is here. So that makes this 90 minus alpha, which makes this alpha. So Wx is going to be equal to the magnitude of the weight vector times sine alpha, and that is going to be in the positive x direction, okay? And Wy is going to be equal to magnitude of the weight vector cosine alpha, but guess what? That's pointing down, right? That's in the negative y direction. I'm going to leave it. I'm not going to write the negative sign here because when we add, I'm going to write these as magnitudes, okay? And we're going to apply the negative once we get to Newton's first law and we're adding the vectors together. So let's get to that right now. So let's add the x. That's going to equal 0 since we're at constant velocity. So all the forces in the x, well, we have the weight component, which is positive, pointing to the right. And then we have the kinetic frictional force pointing to the left. And that's all equal to 0. And then if we add up all of the y's, we have the normal force pointing straight up. And then we have the component of the weight in the y pointing down. So our normal force now, again, is not equal to the weight. This time, not because we're pulling the object with some force that's counteracting the weight, but because we're tilted at an angle with respect to Earth's gravity. So we're only feeling the pull of gravity in the y direction, in what we call the y direction, right? Because we made up this coordinate system. So in the direction that we call y, we're only feeling a small portion of Earth's gravity. So we want to solve for alpha. Alpha is our unknown. And we're going to see that on both sides of these equations, or on both x and y components of these equations. So let's go ahead and fill that out. So this wx is positive, and it's w alpha. And this fk is mu k, which is technically a known since it was given, normal force. And then over here, we don't know the normal force, but we know it's equal to the y component of the weight, which is w cosine alpha. So we can take that unknown, eliminate the n, plug this guy right in here in order to solve for alpha. Okay, and that's equal to 0, right? We're still preserving the right-hand side of Newton's first law. And then we want to solve for alpha, so we can go ahead and move this over. We will divide now. Let's divide by cosine. I like tangent better, so I like my sine to be in the numerator, so I don't have to deal with cotangent. And then my w is going to go away and move over to this side. Okay. So what I have over here is tangent alpha is, and these w's go away, mu k, right? So now alpha is simply equal to inverse tangent of the coefficient of kinetic friction. So the angle here that this, incline is at, let's not say that, right? Because obviously the angle that you're sliding on is not something that's variable. What's variable is the friction, coefficient of friction. And so the coefficient of friction is dependent on the angle that you're sliding at, okay? You could write it the other way, but since we're solving for alpha, it's written this way. But in reality, what's going to change is the coefficient of friction, depending on how much, angle you have and how much gravity is assisting you down the hill. But it's only going to change so much, right? Because there are some physical limits of what the coefficient of kinetic friction can be. So, for example, you're on a snowy surface. You're going to be able to slide down a shallower hill than if you were on, grass or dirt, right? The angle required to get you to slide down on your own on a high friction surface is going to be much higher. So this is an interesting, relationship to think about in terms of reality, right? And the different materials that can help you slide down faster and on a shallower incline. So the problem-solving steps again, right? We're using information from the y component to solve for our unknowns. I'm going to skip this example, but I think you should do it. So basically, now we're accelerating, okay? And so now when we add up the forces in the x and the y, it's going to be equal to ma. Well, the acceleration is, we have to be careful, right? Because the acceleration is on the x. Yeah, so ma is here. And then you're not accelerating in the y at all, right? Because of how we define our coordinate system when we're on an incline. So you're going to have different Newton's laws that you're applying to the x and the y. All right, but then you're going to follow the same problem-solving steps. You're going to use expressions in Fy to plug into Fx to solve for A. So let's talk about another type of frictional force, and we're going to call this type of frictional force fluid resistance. Fluid resistance is a force that acts on an object in a medium, and that resistance or that friction is dependent on the speed of the object. And so fluid resistance can be air resistance, because I don't know if you knew this, but air is technically a fluid, right? It's not a liquid. Air is not a liquid, but it is a fluid. So think about that. Google that. It's interesting, right? It's like, what? Air is a fluid? Yeah, it sure is. So when you're moving in air and you want to start including air resistance, if you're moving in water, if you're moving in a gas, if you're moving in a cloud, right, there is actually a frictional force that, again, points opposite to the direction of motion. But the interesting part of this type of frictional force, which is a fluid resistance, is that it is proportional to the velocity of the object squared. So this is another type of frictional force. It's called fluid resistance, so we could call it F of F, okay? And it still points in the direction opposite to motion, just like regular frictional force, except its magnitude is not mu k times the normal force. Its magnitude is the letter D, which is a coefficient, the drag coefficient, times the velocity of that object squared. Okay, so that gives us the magnitude of this fluid friction or fluid resistance that is acting on an object. And there's a special case of fluid resistance, and that is when you have an object falling in air, okay? And when it's falling in air and the object reaches a terminal speed, okay, it stops accelerating, in other words. It reaches a speed, the fastest speed it's ever going to get. That happens because this drag force, okay, or fluid resistance or frictional, fluid, however you want to call it, however you want to think about it, the magnitude of it, this FF, ends up being equal to gravity, okay? So when all the forces in the y direction sum to 0, that means you're moving with constant velocity, right? You're no longer accelerating and you've reached a terminal velocity, right? Or a terminal speed. So that is the fastest you're going to move in that air. Okay, you can't move any faster. You can no longer accelerate because of that resistance. And so think about this, how it's different from the free fall that we were doing earlier in the chapters, right? In free fall, we assumed there was no air resistance, and that object that we were throwing, it was going to keep accelerating until it hit the ground, right? Nothing was slowing it down. It was going to accelerate and go faster and faster and faster until something physical was stopping it from moving. But in reality, that is not what happens. In reality, we have air resistance, and you do reach a terminal speed. So skydivers, when they jump off of an airplane, right, they're not going to keep accelerating faster and faster and faster until they hit the ground. They're going to reach a terminal speed, all right? It's the speed where their drag force equals their weight, okay? You're technically in equilibrium there because you're moving at constant velocity at that time. Oh, here's basically what I explained earlier, right? When there's no fluid resistance, meaning no air resistance, for example, projectile free fall, right, in chapters 2 and 3, the velocity keeps increasing, right? Because the acceleration that's acting on you is negative g. And so that's going to keep changing your acceleration and increasing it in the negative y direction forever and ever. But when you do incorporate resistance, fluid resistance, your velocity will taper off and eventually come to an equilibrium. And that equilibrium is when the sum of all the forces in the y equals 0. The force being the frictional force, the fluid friction resistance, whatever you want to call it, plus the weight equals 0, right? So, the minus signs, depending on what you call up and down, plus and minus, right? So technically this would be positive and this would be negative. So let's do an example. Let's do this example right here. So here's the skydiver. So we happen to know this constant D. We've probably done some measurements. And this constant D for a skydiver in the spread eagle position is 0.25 kilograms per meter. And we want to find the terminal speed for a skydiver that weighing 50 kilograms. So when they're at terminal speed, that implies it's moving with constant velocity. And we know that when you have an object moving in constant velocity, that the sum of all the forces in that direction are going to be 0, right? So we're going to do that. Sum of all the forces in the y must be 0. And so if you're a skydiver and you're just falling due to Earth's gravity, okay, and you have that fluid resistance, F, pointing it opposite to the direction of motion, then those two together will equal 0. And the expression for the magnitude of a fluid resistance force is D times the velocity squared. Okay? That velocity will end up being your terminal velocity because you're moving at constant velocity, so that V is the terminal velocity. So we'll substitute that expression for F. We can solve for V now. And the terminal velocity for a person in the spread eagle position is going to be .44 meters per second. How many miles per hour is that? Yes, I'm using Google. Google. Oh, that's almost 100 miles an hour. So that's 98 miles an hour. So skydivers in the spread eagle position, not in like a dive position, are moving at 100 miles an hour. And that's why it's really important to have a parachute, okay? And to slow you down, right? And increase your drag coefficient greatly, right? To reduce your velocity so that when you hit the ground, you don't break your legs and break everything else. So it's a fun example, right? It's just another type of frictional force. It's a fluid resistance. And the magnitude of the fluid resistance is simply coefficient D times velocity of that object squared. And the direction of it is always opposite to the direction of motion, just like any frictional force. So let's talk about another unique application of Newton's laws, and that's in the situation of an object moving in circular motion. So if a particle is in uniform circular motion, recall that it's moving at constant velocity, but it still feels an acceleration, or it still experiences an acceleration, and that's due to the changing direction of the velocity. So although the magnitude of the velocity remains constant, the direction, as you can see here, is changing, right? It's constantly changing. And therefore, an acceleration is produced. And the direction of that acceleration is towards the center of the circle. So if the acceleration is towards the center of the circle, then the sum of all the forces acting on that particle is going to be also towards the center of the circle. The net force on the particle then would be the mass times the acceleration. And the acceleration here is the centripetal acceleration, which we found earlier as v squared over r. So let's think about a ball that is attached to a string that is being whirled around in a circle, okay? What is causing this centripetal acceleration? Well, that is going to be the change in velocity, right, around the circle. And what then is the force responsible for keeping that particle or that ball in a circular motion? Well, that is going to have to be the tension in that string, right, which points in this direction. So if we add up all the forces on that particle in the radial direction, we're simply going to get the tension in the string, and that tension in the string is going to be equal to centripetal acceleration, right, times the mass of the particle. Because the result of the motion is the centripetal acceleration. That's why the value of this red vector is the sum of all f's, right? The sum of all f's is giving you that mass times centripetal acceleration. It is not a vector that is on the free body diagram. It's actually a result. It's a result of the tension on the string. And so I bring this up because what happens if that tension on the string breaks or that string breaks? Well, then that acceleration is no longer present because the velocity of the ball is going to just keep that ball continuing on its original path. There is no acceleration acting on it anymore, and there's no change in direction, and there's no change in velocity, so the ball will just keep moving in a straight line path off of the circular motion. And so I bring this up because when we look at objects moving in circular motion, we're going to need to identify the force that's responsible for keeping that object on its circular path, such as the tension, or we're going to see shortly here, a friction. And so let's bring up one other topic before we get into some examples using circular motion. You may not have heard this term before, but we're going to bring it up. The book strongly recommends to never use it, even though they introduce it to you as well. But there's a feeling, there's a sensation that we refer to as the centrifugal force. So if, for example, you're in a car and you're making a sharp turn, okay, you kind of feel your body sway as you're in the car, and you end up swaying outward, okay? You end up swaying in a direction opposite to the centripetal force, okay? And that swaying, or that sensation of moving outward, that's not a real force. That is actually an inertial force. So remember, like, inertia is a tendency to keep your body in motion, okay? And so if you are riding in a car and you are accelerating and you're turning, well, your body is still feeling the acceleration before the turn. And so in order to keep you along that path, in order to maintain your inertia, there's a fictional force that arises called the centrifugal force, which feels like you're being pulled outward from the turn. And so a lot of times, we have these intuitions due to our, what we feel in our everyday life, and we try to find a place for them in Newton's laws, but it comes out to be not correct in this application, because when you're riding in a car and accelerating with the car, you are not in an inertial reference frame, okay? Or you're not in a non-inertial reference frame. You are also accelerating. So you cannot apply Newton's laws in a reference frame that is accelerating itself, okay? You have to be an observer from afar, like perhaps on a bridge or on the side of the road, okay? And watching that car accelerate. You cannot be in the car while it's accelerating and apply Newton's laws on yourself, okay? So it's a very tricky concept. And if this interests you, I have some videos that I can post to kind of explain this concept a little bit better. And we're going to look at some examples that are going to kind of highlight this idea a little bit and why it would be incorrect. Okay. So let's look at this example. Let's use this example to refamiliarize ourselves with some of the terms from uniform circular motion. So we have a sled on a frictionless surface, and it has a mass of 25 kilograms. And it's attached to a rope that's allowing us to keep this sled moving with uniform circular motion. And we're told that we give this sled an initial push, and the sled begins to revolve uniformly, making 5 complete revolutions every minute. If that's the case, what's the force exerted on the sled by the rope? So we're going to do apply a coordinate system like this, so that one of the axis direction is along the centripetal force direction. So we'll use the X in that case. And so with the X along that direction, and then the Y being kind of up into, the Y direction is going to be up and down, where down is straight into the center of the earth, okay? So let's draw a free body diagram. So in the Y direction, we have the weight vector pointing down, the normal vector pointing up, and then along the X, we have the tension or the force of that string, okay? So we call it F. It's also a tension. You could call it a tension. And so when we add all the forces in the X, we know that since this sled is moving in uniform circular motion, in the X direction, we placed it along the center seeking line, the center line that points to the middle of the circle. It's going to have a force acting on it equal to the mass times the centripetal acceleration. And so the sum of all the forces, well, the only force acting on it is the force of the tension in the rope. So that will equal MAC. And the question is, what is F? So F, we're solving for F. We're going to have to work on the right-hand side of the equation to figure out what F is. F is equal to the mass of the sled times centripetal acceleration, which would be the speed of the sled squared divided by the radius of the circle. And so, well, we are given the radius of the circle, we're given the mass. What's V? We're given some information that's going to help us find V. What we know is that 5 revolutions per minute is how quickly the sled is making those circles, right? So if one revolution has a distance of 2 pi times the radius of the circle, then 5 revolutions would have 5 times 2 pi radius of the circle, right? So if the sled is moving 5 revolutions per minute, then the distance that it's moving every minute is going to be 5 times 2 pi times 5 meters. And that's every minute. So that comes out to be 25 times 2 pi, 50 pi, 157.11 meters every minute. So we want to convert that to meters per second because that's the SI units for velocity. And that's pretty easy. So 157.1 meters every minute. We're going to multiply that by 1 minute every 60 seconds. And that's going to give us the velocity of that, or technically it's the average velocity, right? It's the average velocity of that sled. 2.62 meters per second. So now that we have the velocity of that sled, we can plug that in up here. Move all this stuff out of the way. I'll put that over here. Right? The mass is 25 kilograms. Our velocity is 2.62 meters per second squared. And then our radius is 5 meters. We can solve for the force now. And we get about 34.3 newtons. So that's the strength of the force, or the tension of the rope on that sled. If that rope wasn't there, if that tension wasn't there, what would be keeping that sled in uniform circular motion? Nothing would, right? That sled would be going straight. Okay, so we refamiliarized ourselves with some terms in circular motion. Let's now apply this idea to, we're going to skip this example, to a car rounding a flat curve. Okay, so we have a sports car rounding a flat curve, and the curve has a radius r. We're told that the static friction coefficient between the road and the tires is mu s. And the question is, what is the maximum speed at which the driver can take the curve without sliding? So let's work on this example in a separate page. So in this example, we're in a car and we're moving around a track. The radius of the track is r. And the question is, what is the maximum speed that the driver can take this curve without sliding? So when we draw a free body diagram of the car, we're probably going to want to make our x and y axis like this, okay? Where the y-axis is going to provide us the normal force and the weight in the negative y. And the x-axis will give us the direction that the centripetal force is pointing. So this car, it's important to note that this car, what is keeping this car moving in circular motion? Okay, what's keeping this car from going straight, okay, and not curving? And that is the frictional force, okay, the static frictional force. This is kind of a strange idea, but when you think about the ball on the string, all right, let me draw the weight vector and the normal vector. When we think about the ball on the string, okay, that tension in the string is what is keeping that ball moving in a circular direction. And as soon as that tension breaks, that ball is going to start going straight. So you can think of the frictional force as being that string that's allowing the car to move in circular motion. If there was no friction at all, the car could not turn and it would just keep going straight. And that's a weird idea to think about. So I find it a little bit easier to think about this frictional force pointing to the right as the string that is holding this car on a circular path, okay? And so that is the only force acting on the car in the X. The centripetal force is a result, right? The centripetal force is a result, so it does not belong on the free body diagram. It's a result. So when we add up all the forces, in the x direction, we simply have the frictional force, static frictional force, because we're not sliding, right? We want to find the velocity that allows the car to turn the curve without sliding in the x. So that is going to be equal to the mass times the centripetal acceleration. And we can expand what these forces are. We know that the frictional force is mu k times the normal force, and the centripetal acceleration is v squared over r. So you may be wondering, why did we set the sum of all forces equal to the centripetal force, MAC? Well, that's because we know that the object, the car, is moving in circular motion and experiencing a centripetal acceleration. And we know that the direction of that acceleration is towards the center of the circle. And we placed our x-axis to be on that direction. So the frictional force acts as that string that is responsible for keeping the car on the circular path. So that frictional force must equal the centripetal force. So now when we look at the y direction, we can use that to find the normal force. So we can solve for v. And when we add up all the forces in the y, it's simply normal force minus weight equals 0. So the normal force equals the weight. And we can plug that back into here. So we have mu s times the weight equals mass v squared over r. Now we can solve for the velocity. And if I expand weight as mg, I can see that my mass will cancel on both sides. And I get mu s rg square root as the maximum velocity that I can drive this car without skidding out, okay? And if I drive it any faster, then the centripetal acceleration will outweigh the frictional force and I will start skidding out. So what are some values? Just to give us an idea, if mu s, I think 0.98 is a common value for rubber and asphalt. A typical turn radius, let's say, I don't know, 100 meters. 9.8 meters per second squared for gravity. Let's see what kind of velocity that gives us. So about 31 meters per second. And in miles per hour is roughly 70 miles an hour. So on a completely flat surface, we're able to drive a car as fast as 70 miles per hour without skidding out. In a circle, that is. So there's some ways that engineers can not rely on the friction between the tires and the road to keep you safely turning on a curved street. And what you can do is you can bank this curve, so you can incline this curve, and that's going to allow the car to make this turn safely without considering the friction between the tires and the road. So when we do an example with a car rounding a banked curve, we're going to have to consider a couple of vectors not being on the x and y axis. So we'll have to carefully decompose those vectors into their x and y components. So let's do that example here, 522. Okay, so let's do this example. So in this example, we have the car turning with uniform circular motion on a road, But now instead of considering friction between the tires and the road, and remember that friction created a force in the x direction, right? Now we're going to ignore friction between the tires and the road and instead bank the road. So we're going to tilt that road by an angle beta. And now a component of the normal force is going to end up in the x direction. And that component of the normal force in the x direction is going to act like the string on the ball, keeping that ball moving in uniform circular motion. So let's draw the free body diagram here. So we're going to have our x-axis, again, be along the radial direction. Okay, actually, let me draw my coordinate system over here. And then our y will be such that the weight is going straight down in negative y. Okay, so we can draw that weight vector straight down in negative y. And the road is banked, right? It's tilted, so I'm going to draw that inclined surface here so that I can apply my normal force correctly. So the normal force is going to be tilted like this. Okay, it's going to be perpendicular to the road, which is at an angle beta. And if I just continue drawing this so that I can see my angles, okay, this is beta right here. And if I draw, I'm going to draw my coordinate system on top of my free body diagram this time because now my normal force is not along the x or the y. So I'm going to need to draw the components of the normal force. The x component of the normal force is going to be along this blue line here, and the y component is going to be up like this. And so how does beta relate to that right triangle that I just made? So we're going to do a little bit of trig here. Let me zoom in. So if this is beta here, then this is also beta. Okay. Then this is 90 minus beta because the normal force is perpendicular to that inclined surface. So that makes these two together equal 90. And so then that makes this triangle up here, the angle in this upper corner, beta. Okay, so if I redraw my normal force triangle, just so that it's a little bit clearer, this guy is beta up here, y component, x component. So now when I find my components, my x is actually sine beta. My y component is cosine beta. Okay, and they're both positive since nx is pointing to the right and ny is pointing up. So now I'm going to add my forces in the x and in the y. So the forces in the x, all I have is the normal force component in the x. There's nothing else in the x direction. And what that's going to equal to is, so basically the right-hand side of Newton's second law is going to be the centripetal acceleration or the centripetal force, right? Mass times centripetal acceleration. And that's because where I placed my coordinate system, right, I made the x direction along that radial direction. So the sum of all the forces in the x, which is simply normal force in the x, is going to equal the mass of the car times the centripetal acceleration. Since that's always in the radial direction, it points directly towards the center of the circle, and I just so happen to have placed my x-axis there. When I add my forces in the y's, I'm going to have the weight vector pointing down, and then I'm going to have my normal force in the y pointing up. And that's all going to be set equal to 0. We're going to apply Newton's first law because we're not accelerating in the y direction. So question is, what's beta, right? I think we have enough information to find beta by just using Newton's second law applied to the x direction. So nx we saw was equal to n sine beta. Oh no, we don't have enough information, right? Because we have this n here. So, well, let's keep going. Let's keep going and you can see that. M, and then centripetal acceleration is always v squared over r. So we don't have, right? This is known, this is known, this is known. We don't know n, so we need to get rid of n. We're going to use equation 2. Okay, and use a substitution. So equation 2 states that, so that's equation 1. Equation 2 states that ny equals w. Well, we know what w is. That's the mass of the car times gravity. Ny, we know what that is. That's n cosine beta. Solving for n so that we can plug it into equation 1 and eliminate the unknown variable. So now plug, oh, that's weird. So plug 2 into 1. So we have our n is mg cosine beta times sine beta equals mv squared over r. So the m's cancel. Sine beta over cosine beta becomes tangent beta. And then I'm going to move the g over. Boom. So beta is going to equal inverse tangent v squared over gr. And so we can find the bank angle that is going to give us a safe turning speed v. Okay, that depends on what radius this turn is. So what's happening here, right? We now have a force in the x direction that's going to act as our force for the centripetal motion, right? We're going to have this force, which is now the x component of the normal force. And that acts as the string. Okay, so remember that picture earlier in the lecture where we had a ball and a string, and the string, or the ball is moving around in the circle, and this tension in the string is what's keeping this ball in circular motion. And when that string breaks, the ball is no longer in circular motion and it flies off, right? So when you're a car and you are trying to keep turning in a circle, you need a force there that's going to keep you from going straight. That's going to keep you in the circular motion. And if that road you're on is completely flat, the frictional force is going to be responsible for keeping you tethered to the center of the circle, right? But when you curve, or when you bank the curve, you introduce a normal force in the x direction, a component of it in the x direction, and you don't need to consider that frictional force. Although, yeah, it is still there. It didn't go away. But the normal force in the x direction takes over and becomes that tether. Okay, so that's example 522. And the other thing I want, to bring your attention to in this example is our x and y, we didn't place the coordinate system along the incline this time. Okay, and the reason we did that is because we knew that the acceleration due to the centripetal motion was going to be center seeking and along the radial direction. And so we wanted to make sure that that force was aligned with one of the axes. Okay, so we wanted to make sure that F centripetal was aligned with one of the axes. Okay, and that's why we didn't put our coordinate system with the x on the incline. And remember, in those frictional problems earlier, the reason why we made our x on the incline was because we wanted our frictional force to be along one of the Cartesian axes, right? So that's the overall problem-solving technique, is if you happen to know the direction that the force is going to be, the resulting force, the right-hand side of Newton's laws, or one of the components on the left-hand side of Newton's laws, you should align your axis to be on one of those, okay? And that just makes your life easier. Okay, so we're going to do one more example, and we're going to apply uniform circular motion, but now we're going to be in like a Ferris wheel type situation in a vertical circle. So in other words, our centripetal force is going to be parallel or anti-parallel to gravity. So let's draw a sketch. We are on a Ferris wheel and our seat always remains upright. When we're at the top of the Ferris wheel and when we're at the bottom of the Ferris wheel, the normal force that is on us due to the seat is going to change, okay? So let's take a look at that. So if I draw my little Ferris wheel here, and we're at the top of the Ferris wheel, okay, and then we're at the bottom of the Ferris wheel. Those are our two positions. So we're going to draw two free body diagrams, one at the top and one at the bottom. So when we're at the top of the Ferris wheel, well, in both cases, our weight's always going to point down towards the center of the earth, right? Because here's the earth. And recall that the centripetal force is always going to be center seeking, right? So it's always going to point towards the center of the circle. But that centripetal force is a result, okay? It does not belong on the free body diagram. It's a result. So we just need to recall what direction it is once we start putting our equations together for Newton's second law. Sorry about that. So let's draw the normal force. Okay, right? The normal force is the force of the chair on us. And so that's all we have, right? Except we know that the direction of the centripetal acceleration when we're in this position is going to be down, and the direction of the acceleration at that position is going to be up, right? Pointing towards the center of the circle at all times. So for top of the Ferris wheel, we're only dealing in one axis right now, right? We'll call that the y-axis. So the sum of all the forces in the y, we're going to have n minus w, and that's going to be equal to the acceleration pointing downward, which we technically always call that, right? If this is our x and y, downward is going to be negative. So the acceleration due to centripetal motion will be downward. So the force that we experience due to centripetal motion will be negative m/ac. And so then when we solve for the normal force, we're going to have negative m/ac plus w. So that's at the top. I'll call that nt. At the bottom, we add all the forces in the y. Again, normal force is pointing up, weight's pointing down, but this time our net force is going to be up because we know that the acceleration due to centripetal motion is up, okay, which is positive. So we're going to have a plus mac here. And so then when we solve for our normal force at the bottom, we're going to have mac plus w. And so what you can see is that you experience a greater normal force when you're at the bottom of the Ferris wheel than when you do at the top. And that's because of that net force acting on you is equal to your centripetal force due to your motion and your circular motion. And centripetal acceleration and centripetal force always point towards the center of the circle. We could further refine these answers to include what the centripetal acceleration is, and that's, of course, v squared over r. So you could definitely substitute v squared over r into that solution here and here, okay? Especially since those are given in the problem. So that wraps up the last example that we're going to do in this chapter. And to summarize, we basically took a lot of different situations and applied Newton's laws to them. Okay, so we looked at sliding on an inclined surface with and without friction. We looked at cars moving in circular motion with and without friction. We looked at cars moving in circular motion on a banked surface, which puts that normal force having a component in the acceleration direction. And then we also looked at uniform circular motion in a vertical circle, where now you have gravity, weight due to gravity, and your normal force in the acceleration direction.